people, and of course, I want to thank the senior people who have sort of contributed most of this in terms of ideas and like talking to. Okay, so what? And I'll post the pictures more on slides. But it's not the last time these pictures. So the outline of the talk is basically that we separate into two talks. And the first talk is going to be about non-interactive systems and how you classify and construct flat bands. And the second talk is going to be about what happens when you add interactions, either repulsive or attractive, to some of these flat bands. A kind of a subset of them that appears in special models, but they can also be generalized, for example, crystal biographic. And it turns out that some of these physics is fascinatingly exact to solve, given the interaction case, at least for the ground state and for the excitations. So that's the outline. And please interrupt, all over the talk, just as if I was the person. So I'm going to start talking about the different types of flat bands, and the ones that we'll be focusing on are the ones that are not atomic. And then I'm going to talk in the first talk about how to construct flat bands on a lattice, and what we claim is kind of a generic construction if you don't have particle Hall symmetry. So, and then I'm going to end hopefully with the catalog of flat bands of stoichiometric lattice materials, which some of our collaborators in the chemistry department, for example, are growing out and other places. Okay, so this is kind of I kind of don't need to do this introductory slide, or introduction that happens at the school, but I will, because I'm going to emphasize the topological aspect of flat bands. So it was basically shown by several people, starting with politics, that the superconducting pairing temperature in flat bands, for example, if you have a negative interaction, differs very much from the PCS exponential form, and it's basically proportional to the interaction, right? So in the PCS we have an exponential 1 over density of space interaction, and now it's proportional to the interaction. And this is a very clear difference that flat bands give you, and it's due to the lack of really a firm surface in at least the non-interacting flat bands. And then, of course, there's been many other works that look at interactions added on top of the zero kinetic energy flat band. And these works, seminal ones are Mielke, and then Kubert and others, but only kind of very recently, and really with the starting by the seminal paper of Heidi Torma and her Finnish collaborators, it was shown that topology actually plays a big role in these flat bands. In fact, it was shown that the superfluid weights in Chern bands, so in band of Chern number 1, can be bounded from below by a topological bound, and has to do with something called the quantum geometry of flat bands, which we'll also emphasize here. And in the second part of the talk, we'll give a clearer definition of what's actually bounded. It turns out, the Cooper mass or the Goldstone stiffness, etc., is bounded by some quantum geometric object. But for now, we'll just be vague about it. But I'll emphasize the topological aspects of bands. And to start off with this, I wanted to basically point out that there's no yet generic construction for flat bands, and we'll try to give one based on a generalized leap. I'm not sure if any of the audience are listening, but we're on a generalized leap construction. Now, what we're going to be interested in are the set of bands to the right of this line. We're not interested in atomic flat bands, and we're not interested, I'm just going to close the window here, sorry, this is kind of impromptu. It's probably more than review. But so we're not going to be looking at flat atomic bands, which means bands whose flatness of the spectrum comes from the fact that they have zero hopping parameters. So in a flat atomic band, you have very localized orbitals. These orbitals create zero overlap between them, and they can create a flat band. For example, this flat band with this material, there's thousands of them like this. This flat band with this material is due to the fact that the orbitals are actually not well. They're actually very well localized, exponentially localized. They're not they don't interact with one another. They don't hop from one another, and hence you have a flat band because you have no hopping. What we'll be interested in is actually situations where the hopping is quite large. These situations can happen in several circumstances. Either in a topological material, you cannot have topology by having zero hopping because that would create only localized orbitals, and topology is exactly the opposite of localized orbitals. So we'll be interested in topological bands that are flat, and these bands, as I said, have to have very strong hopping. So the flatness has to come from something else than from the fact that you don't have any hopping because you have very strong hopping. And we'll be interested not only in topological bands, which have to have strong hopping, but also in another series of bands called, for example, atomic constructive bands, which Russell probably talked about a little bit. And these bands basically, in these bands, even though they're atomic, which means you can find a set of localized, exponentially localized fine orbitals, these exponentially localized fine orbitals sit actually in the position where there is no atom. So the electron charge is a quantum mechanical object. Its center can move around, and these atoms, the center of charges can sit in some places where there are no atoms. The simplest example in chemistry is covalent bonding. And in some of these cases, we can also get non-trivial quantum geometry of the wave functions, meaning that a wave function at some momentum k differs from a wave function with momentum a little bit away from k. So the manifold of wave functions is non-trivial. So this is basically what we'll be looking at. And obviously, in order to move the center of charge away from the atoms, I will need some hopping. So these flat bands also have some hopping, flat structures on the wings. The only ones that we're not interested in are the flat atomic rings. Of course, the most famous example of a flat band is the Princeton University, which I'm not sure if I'll get to, but I will try to get to it in tomorrow's talk. Okay, so in order to create flat bands, there's a very simple principle, and this is called the line graph principle. And one of the principles, one of the simplest examples of the line graph principle is the Kagome lattice. The Kagome lattice is the line graph of a hexagonal lattice. And every time you take the line graph of a lattice, you're going to get flat bands. Okay, and that's basically the principle. Now, it turns out that this principle is not actually very different from Lee's bipartite principle, as I'll show soon. But for now, we'll just analyze it as it is. And you know, you can go and read about, I'm sure everybody knows that the Kagome lattice is a flat band. But I wanted to show you that there are materials where this flat band is at the current level. So for example, the Jankowski group at MIT was looking at this material, which actually showed up in their paper about the same time when it showed up in our catalog. It turns out this is in the same category of materials, which basically have Kagome planes, and they have these very, very flat bands. That's the Fermi level. Now, Kagome planes in some other direction, they're layered, they're flat in all directions. But you can find 3D line graph lattices with flat in all directions, even though they are strong. Okay, so the Kagome principle will give you flat bands. It exists in the literature, in the literature in realistic materials. What else is known about flat bands? And there's quite a body of literature that's known about flat bands. And one thing is that in order to create term into dimension, term exact pattern. So by exact, I don't mean exponentially small bandwidth and exactly zero bandwidth. You cannot do this with finite range topics. And there are several proofs of this statement by some permutations of these people. And you either need infinite range topic or many bands or infinite number of bands, etc., to get exact flat bands with a term number. Now, I don't have a proof for this, but I think it's the same for every strong topological state. And if somebody can find a proof for this, that would be quite beneficial because then we wouldn't have to look for them. So every stable topological state will have the same problem, I believe. Don't bank on the statement, but I believe that every stable topological band will have you won't be able to get it flat unless you add infinite range topics. Okay. Then another thing for the Kagome lattice flat bands, Bernevig and Downs wrote lattice extended states for these flat bands. So these are the Kagome flat bands. They wrote lattice extended states, which they attributed to this degeneracy point. So in the Kagome, because it's a line graph by part-type lattice, you get this degeneracy point between this dispersive band here and the flat band. And then Bernevig and Downs tried to get the basis for the flat band plus the degeneracy point, and they found that you cannot get it to be localized. They attributed them to the degeneracy point, but in fact, they can be attributed to the flat band also. Then the Howe group at Princeton basically has, in a series of papers over the past years, has a series of models with many flat bands. For example, look at this model on this lattice. Okay, and this model has flat bands here. When it's, I could embed this model in another lattice and get more flat bands, another second, etc. And actually, it has two flat bands here, this model. And this is where we entered kind of thinking about these flat bands. And along with the Howe group and with Princeton too, we looked at these models and found that a lot of these models, the bands the flat bands are topological. Okay. So, in other words, if you do what's called the Wilson group, which is just a very phase of however number of bands you have. If you have two, you're going to get two eigenvalues. You can see I have one eigenvalue of the Wilson with the other eigenvalue. You take the very phase in one direction and then plot its eigenvalues as the momentum swipes the other direction as a function of the. And what you see, for example, here is the eigenvalues. And this is a clear example of these bands are topological. It turns out that, in fact, in a lot of cases, not in all of them, this turns out to be the case, that the flat bands are topological. It's not in all of them. Now we understand why not in all of them, why only in some of them. These bands turn out to be topological. In fact, moreover, we can show something else. If you take if you take the graphing, you do the line graphing, the hexagonal lattice with the Kagome, and then split this degeneracy point by small spin-orbit coupling, for example, what you can say inversion symmetry, then what you find is that, number one, the flat band doesn't stay flat, quite flat, it has a little bandwidth. But number two, and this is the most remarkable thing, you find that there's only one phase for the flat band that can be in, and that's a quantum spin-Hall space, if you keep inversion. If you keep inversion and you gap by spin-orbit coupling the degeneracy point of the Kagome lattice, you cannot gap it true. And that's a fundamental thing that you can prove. And it kind of points out to a deeper principle of why a lot of the flat bands turn out to be topological in the sense of having a Wilson group that winds, and then the flat bands that are flat without SOC, when you add SOC, they also tend we'll go through these things. But in order to go through these things, and I have to turn on the light too, because it's late where I am, much better. So in order to go through these things, we need to do an intermezzo and to understand how you can go from real space orbitals to Brianza eigenvalues and topological bands. So it turns out that by knowing that the real space orbitals, you can A, find the eigenvalues of the bands given by these real space orbitals in momentum space, and B, you can find if the band is topological. So let's see how we do this, and this will help us in showing that that it's natural for flat bands to come out topological. It's not always true, but it's natural. So let's see how we do this. So basically, what I want to point out is that there's a constructive method of going from orbitals in real space to the band structure in momentum space that those orbitals give. And that's just called representation, induction, and then subduction. So what you have is you start with a series of orbitals. And if the orbitals sit on sites, they are, by definition, localized, exponentially localized on site. The orbitals of atoms have exponential localization. If I make them sit on site, they're exponentially localized. If I take all the orbitals in material, the bands associated with all those orbitals, all those bands together, they have to be non-topological because they're associated with all the orbitals and these are exponentially localized. A subset of them can, however, by band inversion, become topological. That's another story that we'll see in 3 slides. But basically, in order to see how you can get from orbitals to the eigenvalues in momentum space, what you need to do is you start with the representation of the orbital on site. For example, there's in graphing I would have the PZ representation, the PZ orbital representation. In Bismuth I would have PX and PY orbitals. Then you induce it into the space group. This is the entire space group. This is a large representation, okay, which basically tells you what you did out of taking an orbital and translating it on all the lattice sides of your entire lattice. This is a huge matrix. So then all you need to do in order to find the eigenvalues at high symmetry points is to do representation subduction, or in the Fourier transform. So you need to do representation subduction at a point in the Briand zone. For example, this K can be gamma, big K in the case of graphing M, etc. And then by representation theory, we know the composition of this representation into EREFs of these point symmetry groups. Okay? So in this case, for example, for graphing, no matter what the hoppings are, if I keep C3, C6V symmetry, for example, I will get a drop point here. No matter how, if you have 100 billion atom range hoppings, which are completely unnatural, I will still have a K point. Here, this just comes out of representation induction. But let's see how you do one of these things. So this is very formal. Let's see how you do one of these things in a realistic system. I'm not sure if you can see this with the big dark. But for the simplest case, with inversion symmetry, we can do this by hand right now on the board. Okay? So I'm going to give you an example of how you get from orbitals to the Briand zone eigenvalues of the bands formed by these orbitals, by these localized orbitals. So I'll start with localized orbitals. I want to get the Briand zone eigenvalues of the bands formed by these localized orbitals. I'm going to give you an example of how you get that for the inversion system. Okay, and let's start with the 2D lattice with inversion symmetry. Okay, inversion symmetry just changes my R to minus R. So it turns out I have 4 spots in the unit cell, okay, that are special. And these 4 spots are special in real space because they remain invariant under a transformation. So, for example, the origin of the unit cell is special, right? Because it remains invariant under inversion, right? And I can ask what kind of orbitals can I put here, and the orbitals I can put here have to be representation of inversion. So there's only inversion is a Euclidean group, I squares to 1. There's only two representations, the scalar and the vector, or the I equals 1, which is called S orbital in this in chemistry, or Px, or Py, or Pc, which is eigenvalue -1 because you have a plus and minus. Okay. So now we know that we can put two orbitals on this side. We can either put 1 or S or Px or any combinations of them. You know, imagine an atom that has many combinations of this, and I can put S or Px or SS or Px. Doesn't matter. So what we'll ask is, what are the bands formed first by the S orbital at this position? These are called Rickle positions, and this is the 1A Rickle position. And then we'll ask, what is the band formed by Px orbitals at this Rickle position? And it turns out that the bands formed, if I would take two S orbitals and 500 Px orbitals, would have the same it's a vector space, so it would have the same eigenvalue as if, you know, I just form a band by two S orbitals and 500 Px and add them up together. So this is the first special point in the unit cell. There's another special point in the unit cell, and this point is the mid bond in the x direction. Now, what you notice here is that the mid bond in the x direction is invariant, but is invariant under a group. But this group is different than just inversion. Why? Because once I pick my origin, inversion takes me to this mid bond here, okay? And now, in order to get back to this mid bond, I need to perform a translation by an x unit cell vector. So the group, even though it's isomorphic to Z2, is a bit different. And this difference is going to matter in the mental space when the representation of translation is going to be phases. And you'll see this difference. Okay? So I can still put on this side, okay, on this mid-bond side, I can put orbitals, or I can consider center of charge that can be there, etc. And since this is still a Z2 group, I can put, this still squares to 1. I can put either S or Px orbitals there too. But it's S or Px under this transformation, okay? And when I Fourier transform it, this transformation, it gets a phase. It gets an e to the ikx. So now, while this guy, which sets at, while bands coming from S or Px orbital, which sits at the origin of the unit cell, in momentum space would get no phase. So the S orbital in momentum space, I would have the gamma points, the x points, the m points, and the y points, which are invariant under inversion. And since I have no phase for the S orbital, then this guy would be plus, would have eigenvalue plus here, plus here, plus here, plus here. The Fourier transform has done nothing, so I have no phase. However, here, the Fourier transform has done something, okay? And the S orbital would have plus here and plus here, because kx is 0, but minus here and minus here eigenvalues. So the band induced by an S orbital, but I just said S orbitals, with whatever hoppings you like, would have to have these eigenvalues in the mental space. Of course, the P band would have, you know, minus, minus, plus, plus, etc. So you can do this. There's two more points in the unit cell that are special. There's the one in the y direction, which has symmetry group translation times, inversion times translation in the y direction, and eigenvalues inversion times into the iky, and you know the eigenvalues for this would be plus, plus, minus, minus for an S ray, right? Because if we get at ky equals to 5, we'll get a minus sign, and you have this guy, which is the middle of the unit cell in both directions. This is this middle, which would have, for example, plus, minus, minus, plus at gamma x, y, m as eigenvalues. Okay, so now we're ready to find out all the atomic limits. And all the atomic limits are written here. This is basically just a slide of what I just explained. So S orbitals in that 1A position will have 1 or plus 1 at all the high symmetry points. P orbitals sitting at the 1A position, there's no sign change, will have minus, right, at all points. Now, if you sit at the 1B position, right, you'll have a translation in the x direction, so you have minus, minus, plus, plus, right? You have a k x equals to 0, you have plus for an s orbital, and minus at kx equals to pi, and so on. So, first claim is that, and this you can prove, but I cannot prove it here, that all these 8 sets of bands form a basis for the atomic limits. In other words, any atomic limit or any state that has maximally localized Wannier function, we can describe a maximally localized Wannier function, no matter how many of them, as long as they're not infinite, can be written as a linear combination of S and P orbitals at these 4 spots in the lattice, or in momentum space can be written as a linear combination of all these wave functions. Here, I've just basically performed the induced representation that I was telling you about. Now, that's statement number 1. Statement number 2 is you immediately notice here that these atomic limits have something special in the sense that they all have an even integer of negative inversion eigenvalues in the Brion zone. Okay? And this even integer is, for example, 0 negative eigenvalues here, 4 here, 2 here, etc. But it's always an even integer. So now, if you find a band that has an odd number of inversion eigenvalues, then you know it's topological. And this is the Z2 index, which is the inversion eigenvalues even or odd. Okay, with time reversing the Kramer's pairs. So it's just a generalization of this. This band, you know that if I have a band with an odd number of minus eigenvalues, it can never be written down as localized orbitals, because I have my localized orbital basis here, and the localized orbital basis here has only even number of negative eigenvalues or positive eigenvalues. And you know that this band is then topological. In fact, it turns out that this is a Chern number band. It has to have an odd Chern number. You know, to find out the exact type of topology and exact consequences, such as edge states, etc., we have to go a little bit further. But this kind of exercise immediately shows you that you can return all the atomic limits. So everything that can be written in terms of localized orbitals is a sum of these induced representations whose eigenvalues at high symmetry points are known, and immediately tells you how to build that something that's not a sum is topological, and you get an index from there. So we'll use this intermezzo to show that the flat bands are likely to be topological. So any questions up now? Or is this all very clear? That's a wonderful job.
Sorry, oh, sorry, one question.
Can we have other orbitals such as the P0 or P? Can we have other orbitals the 4 point such as the Py or Pz?
Right. So depending on your so this is a simple example. Okay, this is for symmetry group P1 bar. So in nature you have around non-magnetic groups 230. Okay, and about 1651 magnetic groups. Okay. Now these 230 groups are much more complicated. So for example, if I have a C4 representation, okay, and if I have C4 P, which means 4-fold rotation axis, okay, plus a mirror plane, that will have what I think, if I heard correctly, the sound was not very good, but if I heard correctly, that will have what you want. For example, you have a 2-dimensional representation where the px and py orbitals are in a 2-dimensional representation. So then all you need to do, the program goes on the same. All you need to do is induce a representation from these px and py orbitals on site. There are two-dimensional representation, but you know how to do representation induction. So you just need to take this representation, shift it around by the lattice translation, whole momentum space, then go to Fourier transform it, put it on the in momentum space from the real space. You take the orbitals, shift them around in real space. That's the induced representation. Then you reduce it at special points in the Brillouin zone, which is what we did here. And the program can be followed exactly the same way. So in fact, now, for all these groups, there's a website called the Bilbao Crystallographic Server where you can go and put in your favorite group and find all these generators of these vector spaces. Does that answer your question?
Yes.
Other question.
Do you know any simple way to get a flat band or in one dimension or quasi one dimension?
Yeah, so flat bands in one dimension, we can get them. So flat bands in one dimension are fine-tuned. I mean, the flat bands are kind of fine-tuned in every system, I guess. So how can I answer your question? Well, I haven't thought, I mean, certainly we can get flat bands in one dimension, like timerized models will have flat bands in one dimension. And now I haven't thought about line graphs that we have, but the problem is that one dimension doesn't have topology.
Yeah.
Unless you put so I think most of the flat bands that you get in one dimension, as far as unless you have particle hole symmetry, most of the flat bands without particle symmetry which get in one dimension are going to be timerized, basically, or some sort of timerization, which are basically atomic flat bands, obstructed atomic. But yeah, I haven't thought with particle hole you can get some. It's an interesting question whether you can get some other flat bands that are not just timerized.
Thank you.
Does that answer your question?
Yeah, kind of.
I think all of them, if you don't have particle hole symmetry, you get a flat band one dimension. It's going to be trivial, and it's going to be basically timerized. More?
Go ahead.
I go ahead?
Yes, go ahead.
Oh, okay, fantastic. Okay, so now we can give a constructive method for flat bands and show why it's natural that a lot of them, not all, are topological. And this is really a generalization of the Lieb construction. Okay, so Lieb said something in 1989. Lieb said the following thing: how can I build flat bands? Let's think about graphs, but obviously this applies to lattices. And said the following: take a lattice that has two sublattices. Okay, a sublattice L of NL sites, and the sublattice L tilde of NL tilde sites. Okay? And put in hoppings only between these two sublattices. Okay, not within one sublattice. Then it creates this Hamiltonian. Okay, and this S matrix, okay, has different number of columns than number of rows. Okay, and then because it has different number of columns than different number of rows. Okay, if I try to find its eigenvalue, so there's data, for example. So here the number of rows is L tilde, so the smaller sublattice. So make L tilde have smaller number of sites than L. So here the number of rows is L tilde, the number of constraints is L tilde, but the number of columns is L. So this clearly has less constraints than variables. So you can always find a normal. Okay? And in fact, by a very simple algebra theorem, you can find NO minus NO tilde null nodes of the system. Now, this is NO minus NO tilde, lattice and one side in L tilde, then I'm going to get one flat band. Okay, so this is 1 0 node per unit cell, and then get one flat band. So we want to generalize this construction, A, because this construction relies on chiral symmetry, and in fact, most flat bands which is material are not chiral symmetric. And there's a very simple generalization that Dimitri did, and this generalization says the following: that if you take Lee's theorem and first of all put any hopping between the smaller sublattice, that doesn't matter. So with any hopping between the smaller sublattice, this BFK is unrestrained. You'll still get the same number of L nodes of 0 nodes as in this theorem. And then you can actually put even hopping within the L lattice, as long as this hopping satisfies a constraint that it has this A hopping here has to have itself a flat band, i.e. k-independent eigenvalue, and the degeneracy of these eigenvalue has to be larger than NL tilde. Okay? So in effect, you can see kind of like you can do a concatenation construction where you build more and more lattices. Put here I could put another bipartite lattice, etc. But the moral of the story is that you don't need chiral symmetry. Certainly, you don't need chiral symmetry in the spectrum of the lattices. And a Hamiltonian that looks, if I didn't tell you this condition, this would be a generic Hamiltonian for any system. Okay, but with this condition, you will get flat bands. This and the spectrum will not be chiral. Okay, and we can. I'm not going to go through this math slide. You can find the zero eigenstates of the bands. Moreover, we claim that basically all these line graphs, split graph, and etc. Lie lattices are basically the same thing. So, for example, if you take the Lie lattice, this is really chirally symmetric Lie lattice. You see the spectrum is chirally symmetric. You get this zero flat band. Okay? But then, what you can do is you can put a chemical potential either on these sides, which goes to infinity, or on this side, which goes to infinity. So let's play that game and put the chemical potential on these sides. This chemical potential is basically going to take these sides out of the contention. It's going to integrate them out, and it's going to form an orbital of either one band per unit cell, which is this guy, or this lattice, which is the more interesting one, okay, which is the line graph of this lattice, the line graph of this lattice. Okay, so you can see that the line, and this as a line graph lattice has a zero mode, and you can see it here, there's a flat band. So you see the line graph construction is just actually the Lie construction plus integrating out, putting large chemical potentials and integrating out bands, and you obtain the following effective Hamiltonian lattice for this band. Okay, so this Lie construction, or the generalized Lie construction, that's kind of a simple generalization of Lie that Dimitri and Aaron did, it was just kind of like a generic method that includes line graph, split graph. But now the beauty of this construction is to explain why when you have flat bands, you're going to get this. You're very likely to get topology. So let's see this. So just remember the few slides ago when I said that just the orbitals in real space, I can get to the representation on the lattice. And then I said that atomic limits or trivial states can be written down as sums of these elementary band representations.
So can I ask you a question?
Yes.
Yeah, I think you didn't rigorously define what you mean by line graph and split graph.
What I mean by what?
Line graph and a split graph.
So the line graph, yeah, about split graph, forget about it for now. The line graph is you just take a line graph is the following. I just take a lattice. So the line graph is just it's basically it's this. Okay, you just take a lattice. Okay, and then sit on the midpoint. Okay? And now you define the following hoppings. The hoppings that you define are based on the rule that if two of the new sides, the line between them, meets or crosses a site on a blue site, okay, then you have the hopping. So for example, between these two sites here, okay, there's not if it crosses, if, sorry, I said something stupid. If between all the sites that are linked to one blue site, there's a hopping. So for example, you get this hopping, because they're linked in the middle site, this hopping, this hopping, this hopping, and this hopping. Okay? So that's how you build the line. For the hexagonal, you just do this. So this, you have the hexagonal, and then you build, so the hexagonal has a atom here, then you put the pentagonal, right? You put a midpoint, which one is the pentagonal. Okay? And then these three sites, these X sites, are linked to the hexagonal site. So then they have a hopping between them. So, and then I'm going to take out the hexagonal site. So then we take out the hexagonal site, and that's the carbon model. So is it clear how to create a line graph model? Okay, very good question. Thanks. Is it clear or not? Have I answered your question? Yes. Thanks. Very good. Okay, so now I want to basically show you why flat band topology is topological. So I said atomic limits can be written down as sums of these basis states that I said that can be obtained in momentum space by writing by taking orbitals, putting them on sites, doing the induction, doing the subduction, doing the Fourier transform, doing the subduction, and I showed you the inversion case. And something that cannot be written as a sum of these bases or of atomic limits is not an atomic limit. Okay, if you can't write a thing down as sums of atomic limits, it's not going to be an atomic limit. Okay, so then the beauty of this construction is that you can prove the following. So let's take here, for example, a generalized flat band model where you can see loss chiral symmetry because this guy is different from this guy. The energy. Okay. So you've lost chiral symmetry. Okay. So what we can prove is the following. Take all the bands in the system. Okay. So if I take all these three bands in the system, now of course this proof is generalizable to any number of bands. If I take all these bands in the system, I know where all these bands come from because I only have orbitals on L and L tilde lattice, right? I only have two lattices, right, in this generalized construction. So all these bands come from these orbitals. Okay? So I have an immediate mapping from L plus L tilde orbitals to all these bands. Meaning I know, given the L and L tilde orbitals, the eigenvalues at the gamma point, the eigenvalues at the K point, the eigenvalues at the M point. I don't know how they're distributed. For example, I wouldn't know that M1 plus is above M3 plus here. I would know because I just said M1. But I wouldn't know that, I wouldn't know how they're distributed. Maybe this guy is distributed above here. But I would know what they are. Okay? Then, the next thing that you can prove, which is very, which requires more time than I so on here to go through proof. But what you can prove is that if you neglect the flat band, okay, then the other bands, which for these systems come in pairs, you can generalize the proof when they don't come in pairs, but then the other bands have the same eigenvalues. So you see the blue bands here have the same eigenvalues as the lower blue bands. Okay? These gammas are just some crystallographic talk. Gamma K and 1, K1 and 1 are just crystallographic talk for some representation. You can go into the bar crystallographic so you can find the eigenvalues. Okay, there you can find the characters, etc. So we know what the representations are, but here we just give some, I answer. I wouldn't be able to tell you the right values. You just go from the Barbara graphic survey and find it. Okay, so what you can show is that the band that's blue, that's non-flat, above the flat band, has the same eigenvalues as the other blue band below the flat band, for example. And they have the eigenvalues, the same eigenvalues that coming from the L tilde orbitals. For L tilde on the L tilde lattice, I have some orbitals. If we can prove that these eigenvalues at high symmetry points are the same as if I took L tilde orbitals, okay, on the lattice, and did the representation induction, did the representation subduction, and found the eigenvalues. So this is an L tilde. This is an L tilde. These are the bands that these are the eigenvalues of bands that will be generated by orbitals on the L tilde lattice, by the orbitals that I put on the L tilde lattice. So I have the following. This is kind of an axiomatic way of representing it. I have that all the bands together, which are L plus L tilde, is equal to 2 of L tilde plus the flat band. So now you can see that this is an atomic limit, right? Because it's an atomic limit of L plus L tilde orbitals. These are atomic limits, both of them. Okay. But now you see that the flat band can be theoretically written. This BR means band representation, which in Zach language means atomic limit, can be written as the atomic limit on the L lattice minus, and this minus is important, the atomic limit on the L tilde lattice. Okay, because I have here only one L tilde, yeah, but here I have two. So when I try to find the eigenvalues of the flat band, I would have to do a subtraction. Because I'm doing this subtraction, it means that most of the time, you see, this is a natural expression. Most of the time, I won't be able to do this. It's not a sum. I'll be able to do it sometimes. If I can deform the lattice L tilde to go to the lattice L, I'll be able to do it. But if I cannot deform it while respecting the symmetries of the model, then I won't be able to do the subtraction and obtain another atomic limit. So the flat band can be written as a difference of atomic limits, not as a sum of atomic limits, and that means it's topological. And you know, it doesn't always show it's topological because sometimes the atomic limit of the lattice L will include the atomic limit of the lattice L tilde. Okay, in which case you can actually do the subtraction, but it's natural, and it certainly is true for small numbers of orbitals, that in a lot of cases, the fact that I can naturally express the eigenvalues of the flat band as a difference and not a sum of atomic limits means that they will come out as topological. Okay, so for example, how does it work? So here I have, for example, two lattices. The L lattice is the S is flat orbitals, and the L tilde lattice is red orbitals. Okay, and this is AG some representation, so that these three F sites, the three F sites are the carbon sites, okay, etc. And this S is orbital sitting at 1A. So this is basically three atmospheres of this one atom solid, two flat bands. And you can see that there are two here because, for example, here I have a M3 plus M4 representation here. And then by going to the Bilbao crystallographic server, you can find this representation induction, which is the band representation of the L. Then you subtract from it the band representation of the L tilde, which is this. And you immediately, just by going to the Bilbao crystallographic server, you can find that it's these eigenvalues. And you can also find that you can have eigenvalues as a sum of atomic limit and then topological. Moreover, we can also see in this case when you have degeneracy points. So for example, in this system, which is chiral, non-symmetric, etc., this flat band comes with degeneracy points. How can I see it? Well, it's very easy to see it because the eigenvalues of the flat band are again, okay, the eigenvalue. So this is the carbon lattice plus an hexagonal lattice on top of it. If I would take this lattice and I would put a large chemical potential on the hexagonal side, I would take this down. I would just get the carbon. Okay. But this is the carbon lattice plus hexagonal lattice. How do I see this deterministic point? Well, it's very easy to see axiomatically. And the way you see it is you just do, again, the eigenvalues of the flat band are the eigenvalues of the atomic sites on the L lattice. So this is the band representation of the L lattice, which is just S orbitals in one carbon, minus the band representation on the L tilde lattice. Okay. But if you try to do this, what you'll find out is that while at the K point and the M point, you'll find that the subtraction works, i.e. at those high symmetry points in the Brion zone, you'll find out that you have, that the band representation of the L tilde is contained at those K points in the band representation of the L. You'll find out at the gamma point is not. So in other words, at the gamma point, you'll find out that you cannot make this subtraction. What you get is a gamma 5 minus a gamma 4. So there's no group theoretical meaning to subtracting representations. So that's when you know that you cannot make the flat band flat without a dispersive band too, and you know you have a Jones point. So if it comes that if by going to the graphic server you find that you cannot make this subtraction like this, okay, in terms of band, you find out that at one K point in the Brion zone, the representation that you get by subtraction is an actual subtraction of representation. It doesn't make sense. Then you have a touching point. If you can make the subtraction, like on the left-hand side, where you get eigenvalues of the flat band, okay, but the eigenvalues of the flat band are not representable as sums at point infinity, then it's topological. And the fact that you have this minus here clearly shows you that it's very likely to be topological.
Excuse me, I have a question.
Yes.
Is it equivalent to say the case on the left-hand side, in the previous slide, is always fragile, and the other one is not fragile for the topology? It has been cut out. Let me repeat my question. In the previous slides,
now I can hear you.
Okay. In the previous slides, you have the two cases. One is without the degeneracy point. The other one is like with degeneracy point. Is it equivalent to say on the left-hand side that the topology is fragile, but on the right-hand side it's not?
So all these are, of course, so I didn't want to get into it because it are more saying, but of course you're certainly correct that with these method of getting flat bands, the most you can get is fragile topology within this minus. At least if I don't have a symmetry. Can you hear me?
Yes.
Yeah. Okay. So this is part of the statement that I made at the beginning, the stable topology. So you see these are finite range hopping models. So and you see that after we do all this stuff, we get a subtraction of atomic units. So this is fragile. But so that's why I said that stable topology needs infinite copies. It's not a true statement, but I certainly believe it. Now here, for example, in this case, this topology is fragile for this band. Okay. Now here, in this case, what you can, on the case on the right, what you can show is that it's got a Jones point. So this guy doesn't have topology. Okay, because it's got a Jones point, and I cannot form the projector into the flat band because of the Jones point. What I can do is remove the Jones, okay, by adding spin-orbit coupling or doing something else, right? Then, as I said, because this is carbon, I said at the beginning that this will go into a quantum spin-Hall state, which I think is the reason why you're asking that this quantum spin-Hall state is stable. But now the difference is that if I add spin-orbit coupling to remove the gap, this band will not be exactly flat anymore. Did I answer your question?
Yes.
So
Yes.
if you want exact flat band with finite range hopping, by this method, which I think without particle Hall is generic, you're stuck with fragile topology and degeneracy points, i.e. semi-metals. If you break the semi-metals, you can get stable topology, open the gap, but that will also make the flat band get slight dispersion. For practical purposes, it might not matter, right? Because the flat, you open a small gap, that's very small dispersion, etc. But since we're trying to make exact same, it doesn't. Have I answered the question?
Yeah.
Very good question. Excellent question. More questions?
So far, okay.
More questions or not? No?
No questions.
I keep going? Or more questions?
No, super.
Sorry, I can't understand.
You can keep going.
Okay, very good. Thank you. Okay. So then it turns out that we can take these constructions and apply them to lattices and ask, which lattices, just by thinking of chemical bonds as, length-based objects. If I have a larger length, then I have less hopping, etc. You can kind of find these type of generalized bipartite lattices and run them through what we have, which is a catalog of about 100,000 stoichiometric materials, and run them to get the flat bands. Of course, if you're going to have a lattice like this, you're going to get flat bands to the spectrum, but then you want the flat bands to be at the Fermi level. And that's the brute force part of what we did, because there's nothing that can tell you where the Fermi level is unless you know the chemistry, you know how many electrons are donated from one to the other, etc. Okay, so you can go to this website now that I wanted to popularize, and you can find all the flat bands that exist in the stoichiometric materials on this ICSD server at the Fermi level. It turns out there's not that many of them actually. With about 100,000 materials, there's only about 300 materials with good, nice flat bands at the Fermi level. And then a lot of them, for example, even if you see that this is at the Fermi level, you're going to need to build into it because this is an insulator. Okay, so and doping will be a little bandwidth. So in terms of very good, useful materials, there's not that many with a flat band at the Fermi level. So if anybody's experimenting this, it's not a comparison with riches here. You get from 100,000 to about 300. There are not atomic bands at the Fermi level. And out of those 300, a much smaller part of them than I think that even 100, I think about 40 or 50, are not known to magnetize. So as you'll see in the interaction part, flat band thermodynamics is ubiquitous. And while that's interesting, obviously we would like to find superconductors. So for the materials that are not known to magnetize at low temperature, out of these flat band materials, there's only 50, 60, something like this. So again, it's not in the bridges, and I would encourage you to check it out. For example, with these types of plots, NM says not magnetic, and you can see the amazing flatness of the band, okay, etc. And you can play around with these type of plots. Okay, so I think I have 10 minutes, so I can start with interactions, and then hopefully go to just the binary tomorrow. Or when should I stop for questions?
You can go for a few more minutes if you want, I think.
I think
Okay.
That's fine.
Okay, very good. So now that we have these constructions for flat band, and these methods I'm going to talk about now are not only for flat band. They apply to other band as long as the interaction is smaller than the gap between the flat band, the bands that we want to look at, and other bands, the Fermi level is in the bands that we want to look at, and the dispersion of the bands that we want to look at is smaller than the interaction. But these are basically projector methods, and these were done by Jonah and Kuka and Heidi. So Jonah and Aaron basically started looking at a family of attractive other models, and we'll get to repulsive ones later in the case of justified error. But the same type of physics applies, okay? Where there's basically analytically solvable ground states. And this interacting part of the top will basically show several things. We'll show that these ground states at fixed particle number have orthogonal non-rate order, so they have to have superconductivity. But moreover, that we can get the excitation spectrum exactly. And we get the electron hole excitations for a set of models, which is called the uniform pairing condition. We can get precisely single particle excitations. We can get the charge 2 excitations, the neutral excitations also, bosones, etc. And remarkably, we see that the mass, i.e. stiffness of these excitations, is related to the topology, but actually to the quantum geometry of the flat bands. Okay. So if I just have an atomic limit, this would not give me any superconductivity or anything interesting as we see that, because I have hoppings which give me topology, which usually bounds the quantum geometry. It's not true only for topological states, for states that also have quantum geometry, but not topology. But for topological states, it's much easier to see because topology bounds the quantum geometry. And we'll see that for these, Cooper, their mass, Boltzmann stiffness, etc., are bounded by something called symmetry. Okay, so what we're going to do is, as I said, we're going to take these flat bands and then project into them. Okay, we're going to consider the interaction project into these flat bands. Now, these projected flat bands have a projection by a Hermitian operator, and this Hermitian operator is just the eigenstates. These are formed by the eigenstates of these flat bands. Okay, so you take your Hamiltonian, i.e., the generalized lead Hamiltonian that we did in the last hour, and you solve the wave functions for the flat band, and you form this projector, okay? And alpha and beta index the orbitals, and if you project into them, then orbitals that you're using are going to be these. Okay? So I start with my electron orbitals, which were these in Fourier space. These are the initial electron orbitals. And then I end up with projected electron orbitals, which are just a projection of these real electron orbitals onto the flat band. Now, you can work either with these orbitals, which are projected real space orbitals, which is no different from basis, or you can work with the eigenstates in these bands. We will do both. In some cases, one of them is more revealing physically than the other. Now, the Hamiltonians that we'll be looking at, these Hamiltonians are so far made up, but they're made up to serve a purpose. And in the case of repulsive interactions, they actually weren't made up, they're cool. But in this case, they're made up to serve a purpose, and this purpose is to give some exact results. Okay? And these, so since we write them down, other people wrote them down before us, we're not going to argue where they come from. Okay? They can come from, for example, strong optical phonon, or something else, but we're not going to argue where they come from. So the first Hamiltonian that we're going to write down has the following form. It's a sort of a Hubbard Hamiltonian, which this is the projected electron operator at position R, orbital alpha, spin up minus the one of spin down. Now, the reason why we write this Hamiltonian is twofold. First of all, we can see that it's part of this indefinite. i.e. it cannot have negative eigenvalues because all these are positive. Okay? So then if you expand this square, okay, so in other words, we know that if we find the ground state of this Hamiltonian, we find the ground state of this. Okay? Then we expand the square, and by using this property, okay, where this is the projector that we gave before in the flat bands, and this is the number operator projecting the flat bands. By using this property, and by requiring what was previously called a uniform pairing condition, i.e. the uniform pairing condition says that irrespective of which orbital you have here, you have many orbitals in this system. Irrespective of which orbital, this number, okay, is the same. Call it epsilon, which is really the number of flat bands over the number of orbitals. You can show that it's just this ratio, this rational number. So the condition is that if this projector does not depend on the orbital, then these two are equal, where you've just taken your positive semi-definite Hubbard model and made it into an attractive Hubbard model. They're exactly the same. So you see, this is an attractive Hubbard model, attractive U on site, and it differs from this by a number operator, okay, a projected number operator. If this condition is true, if the uniform pairing condition is true. Okay, so the equivalence between these two Hamiltonians, if the uniform pairing condition is true, is very interesting because it means that you found, you know, the ground state of this positive semi-definite Hubbard Hamiltonian, which is, we'll see, it's easy to find because anything that's got energy 0 will be the ground state of this because it's positive semi-definite. Then we found the ground state of the negative U Hubbard model. Okay, we found the ground state of a model with something that we know should superconduct because it's an attraction. Okay, and before we go to actually proving the ground state, I want to show you that the uniform pairing condition, because you might think it's pulled out of the hat, is actually natural in some systems. So, for example, Jonah and Aaron and showed that uniform pairing condition can come from symmetry. So for example, if I have a system where my orbitals are related by some symmetry, such as the graphing model, honeycomb to position. Okay? If I have these two orbitals which are related by C6, then by symmetry, I'm bound to have that these condition where now alpha is A or B. Alpha can be A or can be B. Okay. This condition is true. So anytime I have, one orbital spinful per site, spinful orbital per site related by some symmetry, by some crystalline symmetry rotation, this condition will be true. So uniform pairing is guaranteed by some space groups, and you can classify the space groups where the uniform pairing is guaranteed. These models, have some assumptions in them, but it turns out the assumptions, such as uniform pairing, are kind of natural in some lattices and with some orbitals. Okay, so I think maybe I will stop here because now if I go further, I'll have to delve into the structure of these Hubbard Hamiltonians. But the moral of the story is that we want to first look at flat bands under this Hamiltonian or under this Hamiltonian, okay, attractive Hubbard model, which is equivalent under the uniform pairing condition to this Hamiltonian, which is a positive semi-definite positive Hubbard model. And because it's positive semi-definite, we can find the ground state of this guy, and then we found the ground state of the negative Hubbard model. We'll show that the ground state and the excitations, like the charge 2 excitations, which can be found exactly, that they have, superfluid stiffness, etc. And then we'll show, if I have some time, how all of this can be actually twisted around, like just by their graphing, where these strong coupling theories that Yao and Nicolau were talking about are basically system definitely comes from the, in effect, becomes a negative Hubbard-U model, but really they all come from having this positive semi that is all this. So this is not very different from twisted bilayer in a sense. Okay, so let's take some questions if there are any more.
Hi, thanks for the nice introduction. So this Hubbard model, if the number of operators commuted, the spectrum would be very simple, right? Like you just put charge.
Yeah.
So what's the simplest intuition for what this non-commutation number of operators does to the spectrum?
Yes, it was, as I didn't understand the latter part, but you're certainly correct. It's a very good question. If I have a Hubbard model that is not projected, right? So this is, let's just go to, let's see if we can go to, let's see if we can do a quick roundup of tomorrow. But if I have a Hubbard model that's not projected, right? So this is, so if I have n I up and I down, right? As you said, right. This is the classical model, and everything commutes. So it's very simple to do, right? So this spectrum, I just take, I just roll the dice to 1 or 0 to everything.
Exactly, yeah.
On the lattice and computes, of course, indexing the configuration might be hard, but computing the spectrum might be tedious, but you can do it. So it's a classical model. Now, the only difference in these models and what makes them non-trivial is the fact that when they're projected, these operators become, call them O, okay? O R prime, and they don't commute anymore, or in momentum space, OQ prime, okay, or the Hamiltonian momentum space is OQ O minus Q, okay? There's a Fourier transform of the projected density, and these don't commute anymore because of the form factor. So this is how they don't commute anymore because of the projection into the flat bands. So this is why I need these flat bands to have, to not be atomic limits. If they were atomic limits, or if they were atomic limits, they would just, have a delta function and project, and I would still get a simple classical model. But because of this projection, because of this projection, basically, they don't commute, the operators don't commute. So the model is not made up of still commuting operators.
I see. Do you know the conditions for it to be quantum chaotic?
Go ahead.
Is it always quantum chaotic, that model?
Well, for these ones with a uniform pairing condition are very special in the sense that you see that the single particle space, maybe I'll get to that tomorrow. So these ones, I don't think they're quantum chaotic in the sense that, like, if I go high in the spectrum, I get the single particle space. Or maybe they will be for a large number of collective nodes. So these models will just give you collective nodes. Okay, so these ones with a uniform pairing condition, you find out that this I'll show tomorrow, that the excitation spectrum is made out of a number of bands with the same energy. Plus, okay? So I think these, now if I take a lot of collective nodes, might be complicated with the collective nodes here, but because I don't have a finite energy, these are exact degenerates here. I'm not sure it's complicated. Certainly the ones that appear in twisted bilayer, where you have, let me just show you some of the spectrum in twisted bilayer. Okay, there's some of the, so for twisted bilayer, it doesn't have the uniform pairing condition that Jonah and Aaron were looking at. So these guys have, so I think Gal and Balash showed some of these spectrum. So, but these, for example, these are the goldstones plus the particle hole excitation. But here the particle hole continuum, and I think here, you get level repulsion, you get quantitative things.
Thank you.
Yes.
But I'm not entirely sure, so take that with a grain of salt.
Yeah, I have a question. Going back to the flat band parts, so the way that you construct it is by subtraction of two atomic limits, right? But there are cases, for example, that your flat band can appear and the other bands around it, they might be topological, right? So if I have a few other bands around it, below and on top of it, which are Chern bands, for example, and my flat band is not Chern band, is it possible? Or in other words, more generally, is it possible to get flat bands when in an L prime are topological?
Right. So let's take. Let me see if I understood your question. Let's say I have another set of bands here. Okay? And now I kind of make a transition between these bands. Okay, like a gap closing, an inversion. Okay, and make this a Chern band 1, the Chern band -1. Okay? Whatever. So I think this is certainly possible. You can play around with them, but it won't influence this flat band. Right? So this band cannot be strong topological because it's always a subtraction of atomic limits. So it has to be fragile. Have I understood your question correctly?
Yes. Well, I'm saying that you, instead of subtraction of two atomic limits, can I have these L and L prime themselves be a strong topological?
No, because you're unless you because you build them from lattices, right? This is a constructive method of building flat bands. So if you want to have L and L tilde to be topological, okay, then you'd have to tell me, right? So we want to start from orbitals, right? That's always the tenet that we want. We want to start from the chemistry is real. Okay, so if you want to start from orbitals, then Chern band, for example, cannot be written down as orbitals, as localized orbital. So you would have to embed the Chern band to something else. Okay, that has the opposite Chern number. Together you will be able to write it as orbital. So you can't have L and L tilde be Chern band because they come from lattices with orbitals. Does that make sense?
Yes, yes. And another question is that, is there any condition to get isolated flat bands? Is there any recipe to get isolated flat bands? Because in the EFT results that we're showing is realistic material data distribution. Most of the flat bands comes really, with a lot of other bands around it, and sometimes they are even mixed, right?
Yeah. Yes.
Can I get isolated?
You're very correct. It doesn't seem, and the reason is a lot of nature likes Kagome, like pyrophore. Okay? And these ones, nature likes Kagome and pyrophore, and these ones have, you can prove that there's a certain method that they have degeneracies. So indeed, you're very right that nature somehow doesn't seem to like isolated flat bands. What you want is isolated flat bands that are topological, okay, or that are, I mean, I guess this one, there's a small gap here, okay, etc. But for example, nature likes a planet that look like this. Okay, this is an isolated flat band. Unfortunately, it's due to the fact that these are very strongly localized on site. Have I answered your question?
Yes. Thank you.
And that's something that I don't understand.
Okay, we have maybe time for one question from the webinar attendees.
Hi, Andrei. I will be reading you a question. So one of our audience members points out that there are some flat bands that are not flat in all directions in the Brion zone. Would those still host these exotic interacting states, or do you think that non-flat is along certain directions? That's well known.
Yeah, so that's an entirely open topic that we are also thinking about. The answer is I don't know. So I have no idea. That's a very good I remember a flat band workshop, I think 3-4 years ago. This question was also asked by somebody very senior. So that's a very good question. I don't know the answer, and I don't want to speculate yet. But I think clearly, if you just have layers, and the other, and the flat band in one direction is flat because there's no hopping, clearly you can have interacting states. Right? There's going to be layered interacting states. If these are gapped, then they'll be stable to hopping between the layers. So I think this type of weak, like weak TIs, like these weak interacting states certainly should exist. Whether something more interesting exists, that's a different story. When you make that hopping large, right? So yeah. So if I start from the layers, clearly some interesting states, layer states that exist. But then I make that hopping large. I close the gap of the layered states. Then nobody knows what happens. But if I was to bet on something, I would say that very interesting things should happen. Every time you have something new, nature doesn't disappoint.
Well, let's all tune back in on Friday for more answers to these questions from Andrei. And with that, our program is all done for today. So thank you guys. And let's thank Andrei one more time.
It's tomorrow, not Friday. I was wrong. See you tomorrow.
Okay, bye.
Bye.